Okay, so now that we have a Brownian motion on 0, 1, we can fairly easily construct Brownian motions on different time intervals, and in particular Brownian motions on all of the positive part of the real line. So the way we do that is that we give ourselves a family of independent copies of the Brownian motion. And we can do that from our construction, because our construction was based on a countable families of IID and 0, 1 variable, and you can take countable families of such countable families and not still a countable families of IID Gaussians, which exist as long as our probability space is appropriate, large enough, and each independent family of N01 IID variables will give you an independent copy of the Brownian. And then all you have to do is put these independent copies together, sum them up in an appropriate way. So let me explain what this formula tells you just with a drawing. The idea is that you have your Brownian on 0, 1, has to start at 0. It does whatever it does for a value of omega, reaches a certain value at time equal 1, and then what you want to do is restart now. So this was a pass of B0, the copy of your Brownian on the interval 0, 1, and here is at time t and for a value of omega, and this here is the value at time 1 of this first copy of your Brownian for this particular choice of the variable omega, and then you want to just add to that the Brownian, the second copy of your Brownian, right? So what I have here is the second copy of my Brownian at some time s in the interval. This was time t, and for the same value of omega, except I didn't start that second Brownian at 0. I started it at the value that the first Brownian had reached at time 1. So I've added to it the value of the first Brownian at time 1, right? And then you could keep going. You reach a certain value at time 2, add an independent copy of the Brownian, reach a certain value at time 3, add that to the next Brownian, and keep on going. So this is the construction of the Brownian on larger time intervals than just 0, 1. There's a little exercise that you need to do to check that this is indeed a standard Brownian. Right? A lot of the properties within one interval will be just trivial consequences of the fact that it's built on Brownian motion on 0, 1. The one thing that requires maybe a little bit of work is to just understand that we do have the properties of increments, even if the increments are like, say, between this s here and an s prime there, that belongs to a different time interval. All right, then you really have to deal with the property of what happens between 2 and s prime with the third copy of the Brownian, and what happens between s and 2 with the second copy of the Brownian. So there's a little something to prove here, but nothing too hard. Okay, so that's the way we get a Brownian, not just on 0, 1, but on all of 0 infinity. Once we have such a Brownian, we're going to start looking at all sort of other stochastic processes related to it. So when we start talking about stochastic process in continuous time, just like we did in discrete time, we need a notion of filtration, and then we're going to talk about processes being adapted to that filtration. The notion of filtration is exactly the same as in discrete time, right? We say that a family of sigma algebra is a filtration if they are nested, and we say that a process is adapted to the filtration if xt is ft measurable for each t. This is exactly what you would guess. Now, there's one little catch in defining a filtration that works for the Brownian motion, that makes the Brownian motion an adapted process, and that's going to be basically defiltration we use throughout this course to study a whole range of processes that are related to the Brownian. And we'll see that that class of processes that you can obtain essentially from linear combinations and limits of such things of the increments of the Brownian is extremely large. So the filtration we're going to use is called the standard augmented Brownian filtration. So one obvious thing we need to do in order to make the Brownian adapted to a appropriate filtration is to define what's sometimes called the natural filtration. So the ft that makes all the ws measurable for s in the interval 0t. Right. It's the analog of what we do when we have like n IID variables, and we define Fn to be the sigma algebra generated by these first n variables. So by doing this, this filtration here will be the smallest filtration with respect to which the Brownian is adapted. Okay, so you would think that this is all we need. Let's just take the smallest filtration that makes the Brownian adapted, and that would be a nice object to work with. Now, for technical measure theoretic reasons, that is gonna cause trouble. We need to make this filtration, so the sigma algebras in this filtration, a little bit larger to avoid getting into technical trouble. So we augment the filtration, we make it bigger in two ways. One, we replace Ft by the intersection of all the Fs for S bigger than T. Right. Now, if the time was discrete, well, this would do nothing. Ft plus will be Ft. But because the time is continuous, it's a priori possible that there is a jump in information, that in an instantaneous amount of time, you all of a sudden increase your filtration. We want to avoid that. So we want to take not just FTW, but FTW plus, which is the smallest sigma algebra, if you want, that contains all of the FSW at larger time. We also want, from a measure theoretic point of view, we'd like the space omega FTP to be a complete measure space, and for that we also need to add the null set. So any set A that may not be in Ft but is included in something in Ft that has probability 0, we want to add to the filtration. So we really take not just the filtration that makes the Brownian adapted, but the smallest right continuous filtration that makes the Brownian adapted, and that makes the space omega FTP complete, and technically it's defined like that. So couple comments about this. First of all, I want to give you some idea about what this augmentation means from an applied point of view. Just realize that we're not doing anything wrong. From a mathematical point of view, the idea of completion is that it helps make things like product measures be reasonable to define. The idea of right continuity is going to make a lot of things that we would like to be stopping times, and they may not be stopping times if we were to use just the natural filtration. So these are the sort of technical thing we want to gain from this augmentation. One remark here, look, if you're not very well versed in measure theory at this stage, don't worry about this aspect of the course very much. We're going to be dealing with this filtration. In a few cases, we're going to need to remember that it's a right continuous filtration in order to prove that something is a stopping time. But there's not going to be any subtle measure theoretic aspect to what we do. So you can leave that aside if this is not something you are very much into at this stage. Just remember that, okay, fine, this is what we use as a filtration pretty much throughout the course. Now, just to give you an idea that we're not doing anything silly. I mean, we could be augmenting the filtration in such a way that we start gaining at a point T really information about the future, and that would be problematic from a modeling point of view. But what are we doing here? So what are we doing in this right continuity augmentation? It looks like this is something about the future, but this is really saying that the information you have at time T, it's the information that is common to every time in the future. So one way to put that is that from an applied point of view somehow is that we do not allow for an instantaneous jump in the amount of information available. And that's reasonable in practice. We don't expect anything to happen in no time at all. So that's what we are doing here. Now, the idea of making the set omega FTP a complete probability space is even more reasonable, I suppose, from an applied point of view. It just tells you that if you have a event for which you may not know if that event is measurable, but it implies that event happening implies that another event occur, and that other event has probability 0, then you're just going to arbitrarily assign to a probability 0 2. And that's very reasonable also from an applied point of view, right? If something implies something impossible, you might as well say that that event itself is impossible. So we are really not, doing anything too unreasonable here, but we are making our life much simpler from a measure theoretic point of view. Okay, so these will be our objects throughout the course. We would be most of the time dealing with a standard Brownian. I might denote it by W. I might sometimes just denote it by B and just say that the time t is any real number greater or equal than 0. And whenever I talk about the Brownian filtration, I would be implicitly referring to this filtration. Okay, based with that, now we have one first stochastic process and a corresponding filtration. Now we're going to talk about general stochastic processes associated with general filtrations, although pretty much all the time in the course, the filtration we would use will be the Brownian filtration. Okay, so in continuous time, our notion of martingale and our notion of stopping times will be exactly the same as what they were in discrete time. So for instance, if you have a process in L2 or in L1, then it's going to be a L2 or an L1 martingale with respect to a given filtration if the conditional expectation of xt when you condition on fs for a smaller time s is xs, exactly the same as what we had in discrete time. And now there's one extra thing that we can discuss now that we are in continuous time is continuity. So we're going to say that a martingale is continuous if it has almost surely continuous paths. So exactly this property that we know holds for the Brownian, the probability of being in the set of those trajectory that are continuous as a function of t, that is to say, for that omega, the function t goes to xt of omega is continuous, that's set as probability 1, right? So the quintessential example, of course, of a continuous martingale is the Brownian motion with respect to its own augmented filtration. But more generally speaking, we're going to talk about martingales that are adapted to a given filtration, and and that's a martingale property. And we're going to be particularly interested in continuous martingales. Okay, now stopping time, well, a random variable, this time with value in 0 infinity, the real numbers, not just the integers, plus the point at infinity, is called a stopping time with respect to a given filtration if the set of all those tau that are smaller than t is in ft for any t. Okay, so same definitions as before. Now, what I'm going to be proving in this chapter is an extension of all these good results that we've seen in discrete time. The fact that you can stop a martingale and it's still a martingale, for instance. The fact that you have LP, or in particular L2 inequalities for the maximal function associated with that martingale. And very importantly, the Dupes convergence theorem for L2 martingales. Now, all of that will hold in continuous time. And the way we're about to prove it is just by taking appropriate limit of discrete processes and applying the discrete process. So in being able to pass to the limit, we're going to need analogs of or an extension of the dominated convergence theorem, right? We're going to need sometimes to go from an almost sure convergence to convergence in L1 norm. So that leads us right now to a small interlude where we're going to talk about uniform integrability. Now, what happens is that the dominated convergence theorem is not going to be good enough for us for some of these limiting arguments we need to run to go from result about discrete time martingale to continuous time martingale. But there is a simple extension of it that's going to do the job for us. So let's focus on that for now. Now, what we call a uniformly integrable family of L1 variable is a family that satisfies the following property. If you take the expectation of z, but whenever z is greater than k, if you send k to infinity, this should go to 0, right? That's a consequence of being integrable. But what uniform integrability tells you is that you can take a supremum over all elements in your family first, and then send k to infinity, and it would still go to 0. So little exercise for you here that's worth doing. Exercise, show that dominated families are uniformly integrable. And that's intuitively quite obvious. If the supremum is actually smaller than the expectation of such a quantity for a fixed variable z, that's what you would get from having the whole collection of variables dominated by a single element of L1, then the supremum is really not a supremum. It's really just an expression like this for a fixed variable, and the fact that this variable is in L1 tells you that the limit as k goes to infinity has to be 0. So being uniformly integrable is a more general condition than being dominated by a fixed L1 variable. But we are about to see that it's enough to conclude L1 convergence from almost sure convergence. That's proposition 3.12 below. That's going to be the main thing we want to prove. There's a little remark before that that's going to be extremely helpful for us, and you can immediately see why if you think of the Dupes convergence theorem. If you have a family that's uniformly in L2, really using that you're in a probability space, you will get that Zn is uniformly integrable. And the reasoning is here. It's just a very simple consequence of the Cauchy-Schwarz inequality. You could do that as an exercise, or definitely you can check that yourself. So every uniformly L2 families of random variable is automatically uniformly integrable. Therefore, we're going to have a nice L1 convergence result without bothering about dominating the sequence Zn, which is going to be very handy because we want to have something to dominate with to start with. So let's have a look at this proposition 3.12 and then prove it. If I have a uniformly integrable family and it converges almost surely, then the limit has to be, the almost sure limit has to be in L1, and the convergence has to happen in L1. Right, it's the same conclusion as the dominated convergence theorem, but I'm not assuming domination. I'm assuming something lighter, which is uniform, weaker, which is uniform integrability, and in particular, something that will be implied by being uniformly in L2. So very helpful for our kinds of purpose. Okay, let's prove this proposition 3.12. So now what have we got? We've got a uniformly integrable family that converges almost surely. We want to prove that the limit is in L1 and that the convergence happens in L1. And that's really going to be a consequence of the dominated convergence theorem and also Faster's lemmas, just a little upgrade of that for our purpose. So let's just prove first that Z is in L1. Now, how do I do this? I have that the limit as k goes to infinity of the supremum over n of the expectation of the Zn whenever Zn is greater than k has to be 0. That's my assumption. So this implies that, okay, there exists a k naught, let's say, such that the expectation of Zn whenever it's greater than k naught, but it has to go to 0. The supremum of that has to go to 0. So if I take my k large enough, this would be smaller than, let's say, 1. Now, I want to look at the L1 norm of Z. May or may not be finite. It's certainly smaller than the expectation of Z when Z is small. Let's fix the k. Actually, I'm just going to take that k. Sorry, I just need to take the k naught that I had before. So, plus the expectation of Z when Z is large. Now, when Z is small, well, it's small. So, this expectation here is certainly smaller than k naught. Now, when Z is large, this is the limit. This here is the limit of this sequence. So, by Fatou lemma, I can say that whatever this is may or may not be finite, but it's going to be smaller than the lim-inf of the expectation of the Zn's whenever they are greater than k naught, right? because what's inside is the limit of this sequence, but the limit of something is certainly smaller than the supremum, so probably much larger. And the supremum, well, we've chosen our k0 exactly to ensure that this supremum is smaller than 1. So this whole thing is smaller than k0 plus 1. So z is indeed in L1. No problem with that. So that's the consequence of factor lemma and the assumption of uniform integrability. Now, do we have convergence in L1 of our sequence Zn to Zn? Well, here is how you prove that. You look at the L1 norm of Zn minus Z. It is the expectation of Z minus Z, of course. So I'm going to start cutting that into pieces depending on whether or not Zn or Z is large. So let's give ourselves some k, positive, let's say, and I'm going to send it to infinity eventually. So I can look at that whenever Zn is small, and then I can look at it whenever Zn is large. Okay, and now the first part here, Zn minus Z, whenever Zn is small, I'm going to be able to handle that by dominated convergence, because Zn minus Z is going to be dominated if Zn is smaller than K. And what about the second part? The second part I'd like to cut into two pieces, which is whenever Zn is large, and that goes to 0 by the uniform integrability condition, and whenever and the expectation of Z whenever Zn is large. Now, okay, so the first term, let's do a remark here. Zn minus Z whenever Zn is smaller than K, for every omega is going to have to be smaller than K plus Z of omega. So the first term, that's what I was saying a second ago, has to go to 0 by dominated convergence. Right? Because I know that Z is in L1, and of course a constant is in L1 because it's even in L infinity and I'm on a probability space. So that takes care of the first term. Now the second term, of course, goes to 0 as K goes to infinity, because the limit of this quantity for a fixed n is certainly smaller than the limit of the supremum of the whole n. And so we know that, and that's by assumption of uniform integrability. So I can send the first term to 0 as I send n to infinity by dominated convergence, and I could send the second term to 0 by sending k to infinity using uniform integrability. Now I have the last term. The problem with the last term is that it mixes Z and Zn, so I don't really know what to say about this at this stage. But what I can say is that the expectation of Z whenever Zn is large, I could cut that into 2 and write it as the expectation of Z whenever Z is large. That I know goes to 0 as K goes to infinity because Z is in L1, plus the expectation of Z whenever Zn is large minus the indicator function of where Z is large, right? That's just triangle inequality. Now, expectation of Z whenever Z is large goes to 0 as K goes to infinity, since Z is in L1. All right, so that's by dominated convergence if you want. And what about the last term? Well, the last term it's also dominated convergence. Actually, no, this is monotone convergence. So this here, now this is just, yeah, this is indeed dominated convergence, goes to 0 as n goes to infinity by dominated convergence, since z times this difference of indicator function is certainly smaller than 2z, right, which is in L1, and this difference of indicator function, because Zn goes to z almost surely, this difference of indicator function goes to 0 as n goes to infinity almost surely. Now you have to take the limits in the right order to finish the proof, and the way you do that, you say, okay, the expectation of Zn minus z, if I take the limit as n goes to infinity, I'm going to get something that is smaller than, what are the terms where I'm going to send k to infinity? Let's check that again. There is this term here, this second term, and that's where I want to send k to infinity, and there is this term where I want to send k to infinity, and then for the other two terms I'm sending n to infinity. So this is going to have to be smaller than the supremum over all m of the expectation of Zn, sorry, supremum, not limit, of the expectation of Zn whenever Zn is greater, Zm, whenever Zm is greater than k, plus the expectation of Z whenever Z is greater than k, right? And now you can send k to infinity, and this goes to 0. So you take first the limit in n, and then the limit in k, replacing any point Zn, indicator function of Zn greater than k, by the supremum, and by uniform integrability, and the fact that Z is in L1, as we've proved in the first step, the entire expectation of Zn minus Z has to go to 0. So that concludes the proof of position 3.12, which is a nice little improvement of dominated convergence that we're going to use a lot in this course to conclude that we always have convergence in L1 of families of random variables that are uniformly in L2 and converge almost surely.